All right, and welcome back to Mr. Gregoris Math. Today we're going to take a look at integration by parts. So we've been doing some integration in class and we've been integrating some pretty basic functions. So those would be functions that we would know easy derivative formats for. But what we run into sometimes is we run into more complicated functions. Now, we've already seen the U substitution as a way to remove when you have a chain rule situation. So if you would have had an integral that would have been the result of a chain rule in a derivative, then you can use a U substitution to reverse that. Integration by parts takes care of actually a different type of problem. So we use integration by parts if our integrand, and I don't know if that's a word, is a composite through multiplication. And so I'm going to give an example of a problem that would require a composite through multiplication. So we'll just do a pretty simple one. We'll go from 0 to 1. We're just going to stick with a definite integral instead of doing an indefinite integral. And we'll do a product. So we'll have x, and let's go e to the 2x dx. And so you can see like, oh, hey, maybe I want to use a u substitution here. The problem is if we use a u substitution for like 2x, then we're going to end up with u, like u over 2, e to the u. So it's still not going to work quite nicely. We're going to run into that same problem. So we're going to actually have to break this up using our integration by parts formula. So I'm going to calculate our integration by parts formula. Remember, if we have the derivative of u times v, then that's equal to, and I'm just going to use du dv times v, so the derivative of the first times the second, plus dv, dx is what I meant to say here. Probably go back and edit that. So we'll take the derivative of u with respect to x and multiply it by v times the derivative of v with respect to x and multiply it by u. Now what we can do is we can go ahead and integrate all of these with respect to x. So we'll integrate all these dx. Because it's term to term, we're okay with that. So these will cancel out and we'll be left with the integral of those canceled. We've now taken the integral, so we have uv is equal to the integral of, now those will cancel, so v times du, and then these will cancel again and we'll end up with u dv. So this is our integration by parts formula, and we can rearrange this into any way that we like. And so I'm going to say, we're going to rearrange it so that we isolate this particular term. So we'll subtract this one from both sides. So we'll have uv minus the integral of v du is equal to the integral of u dv. And so this is our integration by parts formula, and what we're going to need to do then is we're going to need to pick functions v and u from our integration question, so that way we can use this formula. And I know that this looks weird because you're going to be saying, okay, well, I've got an integral that's tough, and that's equal to a multiplication minus another integral. But what ends up happening here is this second integral always ends up being easier. So as we apply integration by parts, if we apply it to a polynomial, we'll see that the degree of the polynomial goes down. If we apply it to an exponential function, well, it just remains an exponential function. So this is our integration by parts rule that we're going to use, and we got it by just examining the product rule for derivatives. So I'm going to erase this part here, and we'll go ahead and pick our functions. So what I'm going to have to do is I'm going to have to pick u and pick dv. Now dv is a function that I'm going to pick, which I will have to integrate to then solve for v. So I need to pick a function that I can easily integrate to solve for v. So I think I'm going to pick this function is my expression for dv. So I'm going to let dv equal e to the 2x dx. Then I'm going to go ahead and integrate this. So I'll integrate both sides. So when I integrate 1 dv, I'm left with v. And when I integrate e to the 2x, I'm left with e to the 2x times 1/2. And just remember and convince yourself that we can go backwards, so deriving it. So the derivative of e to the 2x is the derivative of the outside, e to the 2x, times the derivative of the inside. So that's just 2 times 1/2, and they cancel out. So that must mean my other function here is going to have to be u. And so I'm going to need u and du. So I'll have to start off with u, that's x, and I'll have to take its derivative. So du is equal to, well, would you look at that, 1 dx. So now as I put these things together, I know I've got the integral of u times dv. And it's going to be u times v minus the integral of v du. So let's see how that goes ahead and works out. So we'll substitute this in. It's equal to u times v. And now because this is a definite integral, we're going to have to consider our bounds afterwards. So uv is just x times 1/2 e to the x. So I'll do x over 2. So that's the first expression. And I'm now going to subtract from this the integral from v du. And so the integral from v du is v, and du is just 1 dx. So I'll have 1/2 e to the 2x times 1 dx. Now this entire expression is going to be evaluated from 0 to 1 because my whole integral is going to be evaluated from 0 to 1. Now, this actually has taken a problem that was quite challenging and brought it in to become a problem that was less challenging. I know it looks more complicated, but take a look at the second integral. Now the second integral can be easily calculated, just as we easily calculated the integral of e to the 2x already. So as I was saying, what ends up happening is when you use integration by parts, a polynomial function ends up having its degree go down. So the degree of the polynomial here was 1, and the degree of the polynomial in this spot is 0. So it's nice because if we had like a degree 2 or degree 3, we could just do integration by parts 3 or 4 times in succession and get rid of that second term. So yeah, you may have just heard me say we'll do integration by parts 3 or 4 times in succession. You can fall into the trap of doing infinitely many integration by partses. And you kind of have to know when to stop digging and instead dig up. So we will finish this one off because we're not quite done. But I'm running out of space here, so I'm going to erase my original integration. So these were my integration by parts, and I like this table because it allows me to do a quick crossover for those things, and then beside for those. So that just makes it easy for me to see how to set myself up. So I always start with dv and u, and then integrate for v and derive for u. Okay, so we now have to evaluate this integral. I'm not going to do anything with my first step, so that's just simply going to be x e to the 2x over 2. But now I'm going to integrate 1/2 e to the 2x. So 1/2 can come out, it's a constant, and then e to the 2x integrates to 1/2 e to the 2x. Now, yes, it is plus c, but because this is occurring within a definite integral, we don't need to worry about the constant of integration. And so we're left with 0 to 1 as being our values that we're going to substitute and check. This 1/2 came from factoring it out or removing the constant multiple, and then this is the integral of e to the 2x. So I'm going to substitute, but I see a half common to each of these expressions. So I'm going to remove a half from each of them before I go and do my substitution. It might make it easier for me. So this is x e to the 2x. And actually, you know what? I should have removed an e to the 2x. Maybe I'll remove an e to the 2x from this. So I have e to the 2x, and then x, and this will be minus 1/2. And that's just going to make my expression a little bit easier to go ahead and substitute and evaluate into. So I had an e to the 2x common to each term, so I removed it. That left me with just simply an x and a 1/2. Now there's only one 1/2 because I common factored out those two. And so we just go ahead and substitute. The nice thing to see is 0 is going to change that to a 1. but we'll have two expressions. So we'll do our first expression with 1. So this is going to be 1/2 times, my first expression with 1 is e to the 2 times 1 minus 1/2, or just 1/2. And my second expression I'll do with 0. So that's going to be minus e to the 0, and then this is negative 1/2. And so I've now substituted in my ends, and I just have some simplifying work to do. E to the 0 is, of course, 1, minusing 1/2 from each is leaving us with leaving us with positive 1/2. Though I think I can common factor out 1/2 from each term now, leaving me with 1/4. So that gets rid of those. And this is going to be e squared minus 1. So we paused the video and double check, and I had made an error where I forgot that I had factored out 1/2, but I still have a negative times negative 1, which made this positive 1. So we use this time to double check on our graphing calculators. We could evaluate this integral, and we could evaluate this expression, and we found that they were indeed the same thing.